This is my work on a modified Galerkin-type finite element scheme for representing highly anisotropic fields, where we're motivated by problems in magnetic confinement fusion, where we have structures in fields that are highly elongated along the magnetic field lines. And a standard finite element scheme has a well-defined connectivity between the nodes, but this causes an extremely complicated meshing problem with the complex magnetic geometries present in fusion devices. And so we're looking to introduce some level of mesh-free formalism where we have more arbitrarily overlapping domain boundaries of the basis functions. And we're extending something called the flux coordinate independent scheme, which was developed by Ottaviani as a finite difference scheme, to kind of a finite element type method. And specifically, we have standard finite element meshes defined on the domain boundaries, as well as planes of constant coordinate zeta, which are widely spaced throughout the domain. And this coordinate is not necessarily aligned to the anisotropy, but provides a one-to-one mapping with the anisotropy. We then have standard finite element basis functions defined on these planes, which represent the fast varying motion perpendicular to the anisotropy, and a slow varying ramp, which represents the small gradients along the anisotropy. A Python implementation of this has been done, and you can see some examples of what these basis functions look like when mapped along a sinusoidal mapping. And we also have some numerical results, where we show that integration by parts allows a local conservation property to be derived pointwise at the quadrature points, and we've done some convergence testing of Poisson problems with both Dirichlet and periodic boundary conditions, showing good second-order convergence and a great reduction in the number of degrees of freedom required to achieve a given level of computational accuracy.